Welcome back for lecture 3. What I'm going to do here is we're going to review for a bit what we did the last time, review some units, and hopefully we'll get to some significant figures and see where we go from there. So let's review. If you remember, we spoke about prefixes. Kilo, 10 to the third, thousand. Centi, 10 to the minus 2, hundredths, right? Milli, 10 to the minus 3, thousandth. Micro, 10 to the minus 6, that's millionth. And then we did nano, 10 to the minus 9, billionth. Okay? We made a number line to try to help us with our conversions. Once again, you do not have to use the method that I'm showing. Anything that works for you, that doesn't violate the laws of algebra, the Quran, the Torah, the Old Testament, as long as it works every time, do whatever works for you. Got it? So here I'm going to draw a 0. 10 to the 0 is 1. Plus 3 representing kilo. Minus 2 representing centi. Minus 3 representing milli. Minus 6 micro, and minus 9. Okay, so let's do a couple of quick conversions, see if we remember what we did the last time. So let's convert. 1 centimeter is how many kilometers? Now remember our silly rule. If this was bigger than that, bigger is negative, contrary to what we learned. Bigger is negative, so we're going to put a negative power. Now we count the steps. Centi is minus 2. Kilo is plus 3. 5 steps. Fantastic. Let's do another one. 1 nanometer is how many millimeters? Okay, once again, nano is smaller than milli. Milli is larger than nano. If this is larger, the exponent is negative, right? So if it's smaller, if it's larger, it's negative, okay? So where's nano? Minus 9. Where's milli? Minus 3. 6 steps, 10 to the minus 6. Not so bad, right? Let's go the other way, shall we? So let's see. Let's do 1 kilometer is how many micrometers or micrometers. So now we have something that's smaller and something bigger. When it's smaller, the exponent is positive. So where's micro on here? Minus 6. Where's kilo? Plus 3. 6 steps to here, 3 steps to there is a total of 9 steps. All right? 1 dimension. Kilometers, meters, centimeters. Let's do 2 dimensions. Two dimensions. So let's do something simple. 1 meter squared is how many centimeters squared? Okay? Well, meter is here. Centi is here. A centimeter is smaller than a meter, so it's going to be a negative power. Okay? But before we do the square, let's just do a single one. 1 meter is how many centimeters? Well, clearly, here to here is 2 steps. We said it's negative, so 1 meter, oh, I said it backwards, right? Smaller is positive. So this would be plus 2. 1 meter is 100 centimeters, okay? So 1 meter squared is 1 meter times 1 meter. So we get 100 centimeters times 100 centimeters. And remember our rule for multiplying powers of 10, we just add them. So we get 10 to the 4 centimeters squared. Squared meters squared. So this would be 10 to the 4. All right? Another one. One more two-dimensional one, shall we? 1 kilometer squared is how many micrometers squared? Okay? Well, this is smaller than that. Remember, smaller is positive. And I'm going to do this in one step because we don't want to waste too much time. Let's look at 1 kilometer and 1 micrometer. Micrometer is 10 to the minus 6. Kilometer is 10 to the plus 3. So what's the difference there? There's 9 steps. 1 kilometer is 10 to the ninth micrometers. So 1 kilometer squared, so 1 kilometer, all right, I'll write it out, is 10 to the plus 9 micrometers. So 1 kilometer squared is 1 kilometer times 1 kilometer is equal to 10 to the 9 micrometers times 10 to the ninth micrometers, and we get 10 to the plus 18 micrometers squared. So square, remember, is 2 dimension. 2 dimensions. Okay? I can erase this. And we'll do a quick 1 or 2 examples of 3 dimensions. Remember, 3 dimensions in length have to do with volume. So I'll write this over here. 2 dimensions represent an area when we're talking about length. We're talking about length now. 3 dimensions are volume. So centimeters cubed, kilometers cubed, meters cubed are all volumes. 1 millimeter cubed is how many kilometers cubed? Well, here we'll skip a step. I'm not going to write it out. But I will say 1 millimeter, 1 kilometer, this is bigger than that. Bigger is 10 to the negative power, remember? Bigger is negative. Kilometer is plus 3. Millimeter is minus 3. The difference is 10 to the 6th. 1 millimeter is 10 to the minus 6 kilometer. So when I cube that, I get 1 millimeter cubed is 1 millimeter times 1 millimeter times 1 millimeter, which is 10 to the minus 6th kilometer times 10 to the minus 6 kilometer times 10 to the minus 6 kilometer is 10 to the minus 18 kilometer. So again, I'll write it out. 1 millimeter, we said, was 10 to the minus 6 kilometers. 1 millimeter cubed is 1 millimeter times 1 millimeter times 1 millimeter. And so we have 10 to the minus 6 kilometers times 10 to the minus 6 kilometers times 10 to the minus 6 kilometers. Our rule for exponents, powers of 10, is we add them, don't multiply. Negative 6, negative 6, negative 6 is 10 to the minus 18 kilometers times kilometers times kilometers is kilometers cubed. So our answer is 10 to the minus 18 kilometers cubed. Fantastic. If you look on our Blackboard, my Blackboard course documents, you'll see many, many practice examples. So good luck, and hopefully you have no life and you could practice it. Great. So let's talk now about scientific notation. No, significant figures. We did scientific. Okay, so let's do significant figures. Okay, SFs, I'll call them. Significant figures, San Francisco's, whatever you want to call them, okay? And I'll explain after we cover the rules on why they're important. Because they come in during when we do experimental science and the accuracy at which measurements are made. All right, let me try to remember the order in which the textbook gives significant figures. First one, all non-zero digits are significant. Okay, so what do we have? 327. How many significant figures? All of them. 3 SFs. All right. 2, 9, 1, 8, 6, 2, 4, 4, 4, 4. Oy, oy, oy. All right. How many significant figures? All of them. How many? I don't know. 1, 2, 3, 4, 6, 7, 8, 9, 10. 10 significant figures. All right. You get the idea. All non-zero digits are significant. Okay. Second, let's see. Zeros between non-zero digits are significant. Okay? What does that mean? Well, let's look. 303. It's between two non-zero digits, 3 significant figures. All right? 927. Okay? Zeros between non-zero digits, significant. Between non-zero digits, significant. So 3, 4, 5, 6, 7, 8, 10, 11, 12 San Francisco's significant figures. Okay? Zeros between non-zero digits are significant. Fantastic. Next one. These are called trailing zeros. Sometimes a little tricky, but not too bad. Trailing zeros are significant only if there is a decimal place. Decimal point, okay? What do I mean? Okay, watch. 300. How many significant figures? Well, there's no decimal place here, so this would have 1 significant figure. 300 with a decimal place, now there's a decimal place. The trailing zeros are significant, so this would have 3 significant figures. Okay? Pay attention to your paper because 3 significant figures. How many now? 1 significant figure. How many now? 3 significant figures. Now, 1 significant figure. So, make sure there's no fly on your paper that decides to fly away because it'll change your answer. 3 significant figures, 1 significant figure. Simple. I want you to note that the placement of the decimal does not affect the number of significant figures. So, let's come over here, rewrite this. We said 300 with the decimal has 3 significant figures. What if I write 30.0? Trailing 0 is significant. Okay, there's a decimal, so again, 3 significant figures. What if I wrote 3.00? Once again, 3 significant figures. What if I wrote 0.300? They all have 3 significant figures. Oops, I snuck in another 0. 3 significant figures, again, the placement of the decimal does not make a difference. Finally, guess number 4, finally zeros to the left. Of the first non-zero digit are, what do you think? They're not significant. Okay, so watch. We said 300 has how many significant figures? Well, trailing zeros, decimal place, 3 significant figures. If I rewrote this as 0,000,300, 3 significant figures. What if I did this? 0.0000000. I'm going to run out of room soon. 0.0000300. Now, how many significant figures? Well, the rule says zeros to the left of the first non-zero digit are not significant. So none of these are significant. We still have 3 significant figures. Okay? So let's write a couple down and see what you get if we agree. Oops. Let's start here. 190. Well, there's a trailing 0, but there's no decimal place. So that 0 is not significant. This has 2 significant figures. Okay? Let's look at this one. There's zeros in between, non-zero digits. There's a trailing 0, but there's a decimal. So they're all significant. 1, 2, 3, 4, 5. This has 6 significant figures. Okay? Let's look at this one. There's a decimal. There's no trailing zeros. There's zeros between. They're always significant. And zeros to the left are not significant. So this has 4 significant figures. Okay? And once again, there's plenty of practice on Blackboard. Let's see how we use this. Why do we care about significant figures? Well, our first equation, really, and we did this in lab, was for mass density. We'll use the symbol D is mass over volume. Now, in a metric system, mass can be measured in grams, kilograms, centigrams, micrograms, nanograms, whatever you want. Here, I'll just make it easy. I'll use grams. Volume, remember, is a length times a width times a height. So it could be centimeters cubed, meters cubed, kilometers cubed, nanometers cubed. I'll just use centimeters cubed for now. Okay? So we're going to write this as D is M over V. Now, for many of us, it's been a long time since we've done math, and so let's just go very slow and review and not be too frightened, okay? Whenever we see an equation, first of all, when we do problems in this class, in any problem, any class, when you do problems and you ask to solve for something, solving means get that symbol all by itself on one side of the equation. And every equation you need to know or be given everything in the equation except one thing. That's the thing you're solving for. But I'm going to rewrite this in terms of numbers. We tend to forget that equations with symbols, the symbols just represent numbers. It's really not that cryptic. Okay? So I'm going to write 6 is 30 divided by 5. Let's look. In this analogy, 6 would be the density. I'm ignoring units. The mass would be 30, and the volume would be 5. Now you agree, I think, that I can simulate, and you can write that divided by 1, right? 6 divided by 1. Nothing's changing. You would also say that 5 is 30 divided by 6. 5 is 30. So what did I do? What I did was I put the V there and the D there. So we solved for volume. M over D. Does everybody see what I've done? It's the same exact thing. And sometimes on an exam or a quiz, sometimes you might want to put in numbers so you get your algebra straight. And certainly 30 is 5 times 6. So that's saying M is just D times V. It's all the same, all the same. This is the level of algebra we'll need. Okay? If you have trouble with the algebra, you can go to Khan Academy and review some of the basic algebra, or you can ask your 4th grader and she'll help you. Sorry. Let's see. Let's try to see how we use significant figures and something like density. Okay? In the lab, let's just make up something. Let's suppose in the lab you have a very accurate balance and you measure your mass to be 12.2222 grams. That's your mass. Okay? So our mass is known to 2, 3, 4, 5, 6 significant figures. Wow. That's a pretty good balance, an analytic balance. Okay? Now suppose we measure volume. Suppose we measure the volume to be 2. 2 what? 2 centimeters cubed. So we didn't do such a good job in measuring the volume. The volume we measure only to 1 significant figure. That really stinks. That's a terrible measurement. So if we want to get density, our calculator tells us the answer is this. It's 12.2222 divided by 2. So our calculator gives us this answer, 6.1111 grams per centimeter cubed. The question is that the answer? And of course the answer is no. Why isn't that the answer? The reason is because our measurement for density can only be as good as our worst measurement for mass and or volume. Our worst measurement is 1 significant figure. That means our final answer must be to 1 significant figure. Thus, the correct answer is just 6 grams per centimeter cubed. 1 significant figure. What if I put a 6 point? Is that the answer? It's the same thing, 1 significant figure. What about if I say 6.0 grams per centimeter cubed? No, not the answer, because 6.0 is 2 significant figures, because the trailing zero is significant if there's a decimal. So we've got to be careful. So now let me give you a tough one. Okay? Let's see how you do on this one. This is a very tricky one, and I'll play with this for a couple of minutes. Suppose I take 2 numbers, I don't care what they are, some things we measure in lab. One number is 3, and the other number is 42.2222. Okay? And we want to get an answer. Once again, our calculator multiplies these. 3 times 40 is 120. So we get 126.6666. That's our calculator. Is that the correct answer? Well, this has 1 significant figure. Terrible. This has 1, 2, 3, 4, 5, 6 significant figures. So remember, our answer can only be as good as our worst measurement. So our final answer needs to be 1 significant figure. How in the world do we round this off to 1 significant figure? Pause the lecture and see if you figure it out, because now I'll tell you the answer. The correct answer is 100. 100 has 1 significant figure. What about 100? No. 3 significant figures. What about 120? No! 2 significant figures. What about 120 with a decimal place? No! 3 significant figures. So the answer is 3 times 42.2222, 1 significant figure, 6 significant figures. The answer to 1 significant figure is 100. Doesn't make sense, does it? But that's the answer. Let's play some more. Same problem. Suppose now I say, what is this? 3.0 times 42.2222. Once again, our calculator gives us this. 126.6666. But that's not the answer, no. Our answer must have two significant figures, remember? So how do we round this off to two significant figures? Well, the closest number we can round this off to would be 130. That's the correct answer. What about 130 with a decimal place? No. Why not? Decimal place means this has three significant figures. Not right. So this would be rounded off to this. Let's play some more. Okay? Same problem, except I'm going to put 3 point, instead of 0, 0, 0. So now I have three significant figures. So our answer must be to three significant figures. How do we round off 126.6666 to three significant figures? Well, this is easy. This is simply 127. What about 127 with a decimal? That's a decimal. Okay? The same. Decimal doesn't change it. What if I wrote 127.0? No, that's four significant figures. Okay? All right. That's enough for today, for this lecture, and I'll see you in a bit.